Hey, welcome back. Today we're talking about algorithms. I know the word alone sounds like something buried in a textbook. But here's the thing. You already use algorithms every single day. You just don't call them that. Let's start with something simple. You're making a grilled cheese sandwich. Butter the bread. Preheat the pan. Bread side down. Add cheese. Cover it. Flip it. Done. That's a procedure. You can follow it once, twice, 100 times. For yourself, for your roommate, for the whole house. The procedure doesn't change. Only the specific sandwich does. That right there is an algorithm. An algorithm is an ordered set of unambiguous, executable steps that defines a terminating process. Let's unpack that. Ordered. The steps have a structure. You don't add cheese before the bread goes in the pan. Unambiguous. Every step is clear enough that no creativity is required to follow it. Executable. Each step is actually doable. And terminating, it ends. It doesn't just keep going forever. That last one is sneakier than it sounds. Make a list of all positive integers sounds like an instruction, but it can never finish. So it's not actually an algorithm. An algorithm must lead to an end. The algorithm versus the program versus the process. Here's a distinction that's important, and it's genuinely useful. Think of an algorithm like a story. It's abstract, the actual ideas, independent of how they're written down. A program is like a book. It's the physical representation of the algorithm. You can print it in Python, or translate it to C, or encode it in a circuit. The underlying algorithm is the same. Only the representation differs. And a process is the act of reading the book, the actual execution of the algorithm on a machine. So, the algorithm is the idea, the program is the written-down version, and the process is the thing running on your computer right now. This matters because the same algorithm can be represented many ways. The temperature conversion formula F equals 9/5. C plus 32 is the same algorithm whether you write it as a formula, as English instructions, or as an electronic circuit. The representation changes. The algorithm doesn't. Real programming languages are fussy. Every semicolon matters. Every type declaration has to be perfect. That's great for computers, but it's terrible for thinking. So computer scientists use something called pseudocode, a notational system where ideas can be expressed informally, borrowing structure from programming languages without the strict rules. Think of it like roughing out a sketch before painting. You're capturing the shape of the algorithm without worrying about the details. Here's an everyday example in pseudocode. While tickets remain to be sold. Sell a ticket. That's it. A while loop. The condition is the thing you check. The body is what you do as long as it's true. When the condition becomes false, you stop. Or this. If not raining. If temperature equals hot, go swimming. Else, play golf. Else, watch television. See how the indentation tells you what belongs to what. That's not decorative. The structure of the code is the logic. Mess up the indentation, you've changed the meaning. Pseudocode also uses functions, reusable bundles of steps. Instead of writing the same instructions over and over, you define them once and call them by name. A sorting function might look like this. Def sort list. Then, anywhere in your program, you can just write sort, the wedding guest list, and the whole procedure runs. Here's something textbooks are honest about. Discovering an algorithm isn't a science, it's an art. A mathematician named George Polya described the process back in 1945, and his framework still holds. He proposed 4 phases. Phase 1, understand the problem. Phase 2, devise a plan. Phase 3, carry out the plan. Phase 4, evaluate the solution and consider whether it could solve other problems too. But here's the key insight. These aren't steps you follow in order. Successful problem solvers often start sketching strategies before they fully understand the problem. Then, if those strategies fail, the failure itself deepens their understanding. You loop back, you revise. The phrase textbooks use for this is, get a foot in the door. Don't try to solve everything at once. Find something you know, some toehold, one small observation that restricts the problem space. At first glance, 2 algorithms can solve the exact same problem and produce the exact same answer. So why does the choice of algorithm matter? The answer is efficiency. A poor algorithm might eventually solve a problem, but it could take far longer than necessary. A smarter algorithm can dramatically reduce time, effort, and computing power. Let's use a simple example. Finding a name in a phone book with 1 million entries. The first method is called linear search. Linear search checks names one by one, starting from the beginning and moving through the list until it finds the correct name. This works, but in the worst-case scenario, if the name is near the end or not there at all, you may need to check all 1 million entries. If each check took just 1 second, that would take roughly 11.5 days. Now let's compare that to binary search. Binary search uses a much smarter strategy. Instead of checking every name, it opens directly to the middle of the phone book. Then it asks, is the name before or after this point? Half of the book is immediately eliminated. Then it repeats the same process, checking the middle of the remaining section and cutting the search space in half again. This continues until the correct name is found. With 1 million entries, binary search needs only about 20 checks in the worst case. At 1 second per check, that's under 20 seconds. So even though both algorithms solve the same problem, one could take days while the other takes seconds. That's why choosing the right algorithm matters. In computer science, efficiency isn't just about getting the answer, it's about getting it faster, smarter, and at scale. Let's say 2 programs both get the right answer. Does it matter which algorithm you used? Oh, it absolutely does. Imagine 2 chefs searching for a spoon. One opens every single drawer in the kitchen, checks, closes it, moves on. The other immediately goes to the utensil drawer. Both find the spoon, but one took 45 seconds and the other took 2. Now scale that up. 10 drawers? Sure, whatever. 10 million drawers? That gap between check everyone and go straight to the right one is the difference between a program that runs in seconds and one that runs for decades. Big O notation gives us a language for this. It describes how an algorithm's running time grows as the input gets larger. Not how fast it runs right now, but how much slower it gets when you add more data. We use n to represent the input size. Here are the main flavors. O of n. Linear. Double the input. Double the time. Like reading every item in a list once. O of n squared. Quadratic. Double the input. Quadruple the time. This happens when you compare every item to every other item. O of log n. Logarithmic. This is the dream. Double the input, add just 1 extra step. O of n log n log linear. Slightly worse than linear, but massively better than quadratic. The sweet spot for serious sorting. O of 2 to the power of n. Exponential. Add 1 item to the input, and the running time doubles. This one kills computers. Here's something that surprises a lot of people. There are problems that are, for all practical purposes, impossible to solve. Not because computers aren't fast enough, but because no algorithm could ever solve them in reasonable time. If a problem can be solved in polynomial time, on, on squared, on cubed, it's called tractable. A computer can handle it, even if slowly. But if the best-known solution is exponential, O of 2 to the power of n, the problem is called intractable. Each item you add doubles the work. The growth is catastrophic. There's a real example from genetics. A database called Alfred stores data on about 1,500 human populations across 1,250 genetic markers. Researchers want to find the largest subset of populations for which complete data exists. To do that exhaustively, you'd have to check every possible subset. The number of subsets is 2 raised to the power of 1,500 times 1,250. That number has more digits than there are atoms in the observable universe. Even if every atom were a supercomputer running since the Big Bang, you still wouldn't finish. That's what intractable really means. Not slow, cosmically, permanently impossible. The simplest approach: just check everything. Start at the first item. Is this the one? No. Next. Is this it? No. Next. This is sequential search. It's ON. For a list of 1,000,000 items, you might check all million before you find what you want. In pseudocode, it looks roughly like this. Select the first entry in the list as test entry, while target value greater than test entry and entries remain. Select the next entry as test entry. If target value equals test entry, declare search a success. Else, declare search a failure. It works on any list, sorted or unsorted. It always terminates. But for large datasets, it's slow. And here's a detail worth noting. If the list is sorted, as soon as we hit a test entry greater than our target, we can stop. The target isn't in the list. We don't have to search to the end every time. Binary search. Now, here's the clever version. Imagine looking for the name John in a sorted list of 16 people. You don't start at Alice and work down. You check the middle. Say you land on Harry. John comes after Harry alphabetically, so you throw away the entire first half. Now you check the middle of the remaining half. You keep halving until you find it or run out of list. That's binary search. Each comparison eliminates half the remaining candidates. Notice something? The function calls itself. We'll come back to that. The performance is O log n. For 1,000,000 items, binary search finds the answer in at most 20 comparisons. For 1,000,000,000 items, 30 comparisons. There's one requirement: the list must be sorted. Which brings us to sorting. Imagine you have a messy hand of playing cards, and you want to sort them from lowest to highest. That's exactly how insertion sort works. Think of this process. You pick up cards one at a time and place each new card into the correct spot among the cards you've already sorted. At first, you only have one card. A single card is already sorted. Now take the next card. Compare it to the card before it. If it belongs before it, slide the bigger card over and insert the new card. For example, you have 5, 8. Next card is 3. Compare 3 to 8. 3 is smaller, so shift 8 over. Compare 3 to 5. 3 is smaller, so shift 5 over. Now insert 3. Result: 3, 5, 8. Then grab the next card. If the next card is 6, compare 6 to 8, shift 8 over. Compare 6 to 5, stop, because 6 belongs after 5. Insert 6. Now you have 3, 5, 6, 8. You repeat this until every card is placed correctly. Why it's called insertion sort? Because each new item is inserted into its proper position in the already sorted part of the list. How it works in simple steps. Start from the second card. Compare it backward through the sorted cards. Shift larger cards right. Insert the current card into the gap. Repeat. Why it's useful. Great for small lists, simple to understand. Works well when data is already nearly sorted. Downside. If the cards are completely random, it can be slow because you may need lots of shifting. The key operation in merge sort is the merge. Given two already sorted lists, combine them into one sorted list. Here's how it works. Compare the first elements of each list. Take the smaller one. Compare again. Take the smaller one again. Repeat until both lists are empty. Let's trace through sorting. 5, 2, 4, 1. Split into 5, 2, and 4, 1. Split 5, 2 into 5, and 2 merge to 2, 5. Split 4, 1 into 4, and 1 merge to 1, 4. Merge 2, 5, and 1, 4. Compare 2 and 1, take 1. Compare 2 and 4, take 2. Compare 5 and 4, take 4. Take 5. Result 1, 2, 4, 5. Performance O(n) log n. For 1 million items, insertion sort could need 1 trillion operations in the worst case. Merge sort? About 20 million. That's a 50,000 times improvement. Merge sort uses a strategy called divide and conquer. The idea is elegant. Instead of struggling to sort a huge list, break it into smaller pieces, sort those, then put them back together. If list has one element, return list already sorted, we're done. Else, split list into 2 halves, list 1 and list 2. Sorted 1 equals merge sort list 1. Sorted 2 equals merge sort list 2. Return. Merge sorted 1. Sorted 2. But wait, step 3 says sort each half by calling merge sort. Isn't that circular? Yes. And that's exactly the point. This is recursion. Understanding recursion. Recursion is when a function solves a problem by calling itself on a smaller version of the same problem. Think of it like this. You're in a long queue, and you want to know how many people are ahead of you. You could count, or you could ask the person in front of you. They ask the person in front of them, who asks the next person, and so on. Eventually, someone at the very front says, 0 people ahead of me. That answer ripples back, 1, 2, 3, all the way to you. That ripple is recursion. Every recursive algorithm needs 2 things. 1. A base case, the simplest version with a direct answer. For merge sort, a list of one element, it's already sorted. 2. A recursive step, a way to shrink the problem and call itself again. For merge sort, splitting the list in half. Without the base case, the function calls itself forever. Infinite loop. You need to guarantee the recursion bottoms out. The binary search we saw earlier is also recursive. It calls itself on a smaller sublist each time. The recursion terminates when the list is empty. Failure, or the target is found. Success. Every loop has 3 components. Initialize, establish the starting state. Test, check the condition for termination. Modify, change the state, so you eventually reach termination. All 3 must work together. Miss one, and you get an infinite loop. Here's a classic mistake. Number equals 1. While open parenthesis, number not equal to 6, close parenthesis, colon, number equals number plus 2. The termination condition is number equals 6, but number starts at 1 and increments by 2, so it goes 1, 3, 5, 7, 9. It never hits 6. The loop runs forever. A subtle bug. A catastrophic result. The modification step has to lead toward the termination condition. In the sequential search, initialization picks the first entry. Testing compares it to the target, and modification selects the next entry. All three are present, all three are correct, so the loop terminates. This is why loop control deserves careful attention even when it seems routine. It's the most error-prone part of the structure. Knowing an algorithm exists isn't enough. We need to ask two questions. Is it correct? And is it efficient? Efficiency. We've been talking about big O throughout, so let's land the key comparisons. Algorithm. The insertion sort's worst case grows as the square of the input. For 1,000 items, that's up to 1,000,000 comparisons. For 1,000,000 items, that's up to 1,000,000,000,000. Binary search on a billion-item sorted list? 30 comparisons. The order of growth matters more than the machine speed. A faster computer running a bad algorithm will still lose to a slower computer running a good one, once the input is large enough. Correctness. An efficient algorithm that gives wrong answers is worthless. So how do we know an algorithm is correct? One approach is software verification, formally proving that an algorithm does what it claims. The idea is to identify assertions, statements about the state of the program, at specific points during execution. There are three types. An assertion placed before an instruction describes conditions that must be true when that instruction begins. An assertion placed after describes conditions guaranteed to be true after it executes. A loop invariant is an assertion that remains true every time the loop's body is executed. It captures what the loop preserves, no matter how many times it runs. If you can prove that these assertions hold throughout the entire program, you've verified the algorithm. This is different from testing. Testing shows an algorithm works on specific inputs. Verification proves it works on all inputs. Testing can miss cases. Mathematical verification cannot. Let's pull back and connect all of this to things you actually use. Search engines don't scan the entire web when you search. They search pre-built indexes using techniques like binary search, which is why results appear in milliseconds instead of hours. Music apps like Spotify sort your library, rank recommendations, and order search results constantly. Every time you see a list ordered by popularity or relevance, a sorting algorithm ran. Databases keep records sorted so that every lookup stays OO log N. Banks, hospitals, airlines, they all depend on this. Without sorted data and binary search, looking up your account among millions would be impractically slow. GPS navigation uses path-finding algorithms to discover routes, the same general problem-solving approach we discussed, but applied to maps and distances. Bioinformatics hits intractable walls constantly. Comparing genetic sequences across thousands of populations means facing 2 to the power of n subsets. No algorithm can crack that. The intractability itself is a scientific result. Let's land this. An algorithm is an ordered, unambiguous, executable set of steps that terminates. It's abstract, separate from any particular programming language or representation. A program is how you write it down. A process is how you run it. Pseudocode lets you express algorithms informally, close enough to code to be precise, loose enough to focus on ideas. Problem-solving is an art, not a formula. Get a foot in the door. Use stepwise refinement. Work top-down and bottom-up. Don't expect to fully understand the problem before you start solving it. Big O notation describes how running time grows with input size. O of log n is remarkable. O of n squared is fine for small inputs, dangerous for large ones. O of 2 to the power of n is a wall that no computer can climb. Sequential search is ON and works on anything. Binary search is O log n and requires sorted data, but finds a target in a billion item list in 30 comparisons. Insertion sort is intuitive and ON squared, worst case, great for small or nearly sorted lists. Merge sort is ON log n, using divide and conquer and recursion, the right choice for large datasets. Recursion solves a problem by calling itself on a smaller version. It needs a base case to stop. Binary search and merge sort are both recursive at heart. Loop control requires 3 elements: initialize, test, modify. All 3 must work together, or the loop never terminates. Correctness can be verified mathematically using assertions and loop invariants, stronger than testing, which can only check specific cases. And some problems, like the Alfred genetics example, are intractable, exponential by nature, impossible in practice regardless of hardware. That's algorithms, both the practical toolkit and the deeper ideas behind it. If this helped, hit like and drop a comment if you want a deeper dive on recursion, Big O, or any of the sorting algorithms. See you in the next one.